You guys study isomers.
Yes.
Yeah.
There's structural, geometric, and what's the third one?
I lied. I don't remember.
You touched on it a little bit.
Structural, geometric, and what is the, yes?
Is it optical?
I don't know. That's a new term for me. What's optical?
At least one carbon bond with 4 different atoms or groups. Is it chirocentric?
Are optical mirror images? Say it again, Alyssa.
It's at least one carbon bond with 4 different atoms or groups with a chirocentric.
Yeah, I think we're talking the same language. Yeah, it would be optical. I'm thinking an enantiomer. And I think enantiomers are optical. Okay, we'll get to it. All right, so first of all, we have structural. Here we go. You need to know this because this is absolutely important because I want to talk about a really, really, really cool geometrical isomer called rhodopsin, which I know none of you know about. Structural. So basically, forget about the numbers. You have the same amount of atoms, but they're just arranged differently. So, is there anyone in the back table who can come up and give me and draw an example of a structural isomer?
Is this resonance? Or is the same one but had a different shape?
Yeah.
Okay. We just learned it.
Can I try?
Sure, Xander, you want to try?
It doesn't contain carbon.
It has to contain carbon.
Then I don't know what.
Okay.
I know what it's in the book, but I can't remember what atoms is where.
All right. How about I help you out?
Okay. Oh,
What is this structure? I mean, does anyone know what this is?
it's creation.
Oh.
Propane. Filling up our tanks with propane. Okay, how can I do this? Propane.
So that's just a structural.
It's a structural isomer.
Okay.
So
It's arranged differently.
Does that mean the shape would still be the same though, or would it be?
Am I doing something wrong?
No.
Okay. It's just if I do, please let me know because I am teaching chemistry right now, and I should get paid more for doing this. All right, so joking. So you can arrange the shape, but it's still so propane has a variety of isomers to it. So an atom of C20H42, you can see how many different isomers it can make structurally. Millions. That's important to biology. Geometric isomers. Same covalent partnership, but differ in spatial arrangements. The reason for it is due to the inflexibility of an equal sign. No, it's inflexibility of the double bond. So that to you may mean well, so let me give you an example. And if I had this, okay, that is one hypothetical molecule or compound. You see the difference of what I just did. This is called the trans isomer, geometric. And this is considered, anyone? Cis.
Oh, that's right.
Oh.
These are geometric isomers of each other, cis and trans. Some of you may have learned this, actually, excuse me, every one of you have learned this from biochemistry in honors biology. And I talked about lipids, saturated fats versus unsaturated fats, and there are cis and trans saturated fats.
That makes a lot more sense now.
Untrans, excuse me, there are cis and trans unsaturated fats. So, there's one example of how cis and trans geometric isomers, same number of atoms, different. Now I want to talk about this, because this is so cool.
What does that have to do with the double bond? It's interesting.
It's the arrangement around. Because when we have, good question, when I looked at propane up here, they were all single bonds.
So you can
Single bonds can break and form. These guys can't break and reform. They stay.
So okay. So you can only move the things not double bonded together.
Correct.
Okay.
Now, I want to talk about this because I like to give biological relevance of all of this gobbledygook that I'm talking about. Geometric isomer. Rhodopsin. That is a pigment that allows us to see visually. In the back of the eye, superior and posterior, which means in the back of the eye and on top, we have a thin structure called a retina. A retina receives light. It allows us to see. If you damage your retina or scar it, you will be blind in that area. If you damage enough of it, it's going to affect the optic nerve and you are going to go blind. Okay? So there is this rhodopsin, and it is a protein. Okay? And the protein can exist in a cis and a trans state. Oh my God. Cis, trans. Trans or cis? Oh my God, I'm drawing a blank. Which one's which? Shh, don't talk to me. Rhodopsin is. I knew I should have looked this up.
You just to Google it. So don't talk to us.
I'm gonna run with it.
None of us are really
Yeah, just think of the mama best.
I want to double check. I don't want to give you incorrect information. Just give me a second. I have to go to page. I got this book pretty much memorized. I know it's in chapter 49. Give me a second. Shh. Just talk amongst yourselves.
I'm gonna have to rewrite my notes. I always write these really sloppy because I'm trying to keep up. So I'm gonna put that on my to-do list this weekend. Rewrite notes.
Okay, got it. So, I'm glad I looked it up because I would have gotten it reversed. So, there are rhodopsin consists of two proteins. This is called opsin, and this is called retinal. Okay? Now, this retinal will exist in the trans state when light hits the retina. It exists in the trans state. If it exists in the cis state, it will not receive the light, send the message to the optic nerve. The optic nerve then sends the message back to the visual association center in the back of your brain, sending the message back to the eye, allowing you to see. So this protein has to exist during the daytime in the trans state. it will then switch to the cis state at nighttime when you don't need to absorb light from the sun because there is no light. The protein rhodopsin then will accept the light, be stimulated, and all of the metabolic events can occur for you to allow to see. Yes.
What does that have to do with like the physical dilation
That's different.
up here?
That's completely unrelated.
Okay.
There's about 100 things that allow you to see. This is just one of them. But I'm just telling you that the biological importance of geometric isomers so you can see that. Xander.
Why does it switch? Why doesn't it just stay in trance? Like, why does it need to switch in the night?
Because the structure determines the function.
So does it have a different function during the night?
It would not register. Yeah, you're not seeing. You're not absorbing light from the because it's dark. The sun's out, so it can switch off. So this retinal can switch to a different shape, which means you don't. Your eye is then going to go through, let's just say, a series of metabolic events that is going to be different than in the daytime. That is not necessary for you to absorb sunlight.
So it just does something else while you're sleeping.
Well, once again, I don't want to confuse you and go down this pathway of explaining the anatomy of an eye. Okay? All I want you to know is that the shape of the protein determines its function. The shape is a geometric isomer in this case. If you want to know further why, I don't want to take class time and go and spend 25 minutes on this. Okay? Because it does get confusing. Alright? But we're just knowing that this will go back to the cis state at nighttime, and then it converts itself back to the trans state, and that allows the cell recognition to occur because the cell is made up of protein. You wrote in your paper, cytoplasm mostly made up of protein. Cody.
Is retinol the only protein that goes with transcyst, or is retinol and opsin that go with transcyst?
Just retinal. Yeah. The whole rhodopsin. Just retinal. All right. Enantiomers. Mirror image. A molecule with mirror images of each other with an asymmetric carbon. Okay. So, an enantiomer is very important because it has this asymmetric carbon. So if this is okay, and then if you notice, this would be the, do you see the difference of an asymmetric carbon? It can shift its place. Enantiomers are very, very important because you can switch the elements around that asymmetric carbon, forming a different molecule. If you form a different molecule, you have a different function. Let's talk about back in the 50s when moms were giving birth, there was a drug called thalidomide out there. Thalidomide was used to allow the woman to have some pardon from morning sickness. But they didn't realize thalidomide had an enantiomer to it. So if the chemistry wasn't right and the drug contained the other asymmetric carbon's enantiomer, that killed the patient.
Oh my gosh.
Many women were dying to be treated for morning sickness in the 50s and early 60s, and they finally realized what enantiomers were. Now remember, DNA was only around, established for about 2 or 3 years. So we're in the embryonic stage of really good science. All right, so we've come a long way. Now, in this you're going to say, well, how did the people with morning sickness are given